Castillo Costin, and he is on his last year of grad school, and he's going to talk about global rational approximations of functions with factorially divergent asymptotic series. Please.
All right. Well, thank you very much. I'm really happy to be here from your neighbor in Columbus. I got this shirt when I was looking into graduate schools, and University of Michigan was one option. It turned out to be between Ohio State and Michigan, yeah. So you guys have been a part of my mathematical career so far, and it's really nice to be here.
So does that pin burn up?
So I actually made the joke earlier that I'm surprised that the universe hasn't actually just fully collapsed into a singularity, but we don't know, right? You know, it remains to be seen. So. Exactly. So as Andre mentioned, I'm here to talk about some joint work with Ovidiu and Rodica Costin. This is a project that resulted in a paper that we finished last year. We submitted for publication. We're pretty close to the finishing the comment or addressing the comments. And hopefully will be published within the next couple of months in Journal of Approximation Theory. So let's get started here. Actually, like to do.
I think the 2 dots, the 3 dots, if you go up there.
Ah, gotcha. All right, so then single page. Okay.
And then if you touch the little, to the right of the 3 dots, it might make that thing go away.
All right, beautiful. Thank you so much. Beautiful. All right. So this is the structure of the talk. I'm going to give you a little sales pitch, a few results from our paper, and then we're going to take a step back, talk briefly about divergent series and a little bit about Borel summability or summation, and then I guess I should have said the title of the talk is about factorial expansions. So we're going to talk about classical factorial expansions and their limitations. And that'll lead us into development of our new method of factorial expansions to improve on those limitations. And we'll get into the the main theorem of the paper, and talk about a few related results. And then finally, we've had some recent work or progress in the direction of the Painlevé project, and we have generated some rational approximations of the tritronquée solutions to P1, and so we'll talk a little bit about those. So our first result is a representation of the classical special function, the exponential integral, defined, defined like this, as a Laplace type integral with a simple pole at 1. And let's see, so here, as we go, these Lurch phi transcendents, we'll have more on them later, but they seem to be at the core of this theory that we've developed, and they in a way carry the properties that we'd like our factorial expansions to have. And so the crux of the method is to place the problem into a form in which the Lurch functions just appear. So we'll have a little bit more about that later. But this expansion is valid for x in a cut plane, and we will see that this is also each of these Lurch functions is representable as a factorial expansion. So this thing turns out to be, or this gives us a rational expansion for the exponential integral. And one thing that's quite interesting is the fact that this direction corresponds to an anti-Stokes line, and we'll actually be able to see the Stokes phenomena with rational approximations, which is something that we thought was pretty notable. Okay, if you'll recall the definition of the psi function as a logarithmic derivative of the gamma function, and we have this nice identity and a few other things that come out of this. And I'm pretty sure there's pretty straightforward application to analytic number theory that we sort of get for free that will hopefully be work for a future project. And finally, in the operator realm, if we're given a self-adjoint operator, bounded or unbounded on a Hilbert space, we have a representation of the resolvent evaluated along the positive imaginary axis in terms of the sampled, or in terms of samples of the unitary propagator that it generates, or the unitary group that it generates. I think this is pretty interesting, and we'll have maybe a little discussion about this later.
What is index J of U? U is index J?
So these are, so from the spectral theorem, we can exponentiate, so given A, so A is some mapping on a Hilbert space, then we define U sub t to be the exponential e to the minus I t A. So then in this case, like U sub j times 2 to the minus k is just e to the minus I j 2 to the minus k A. So they're discrete samples of the unitary, the one parameter unitary group.
But for shorter and shorter times.
Exactly. Okay, so divergent series. If you're, this is something that's been around for a long time. If you're solving a physical problem or ODE or PD, and your approach is by perturbation theory, you might generate a series that has zero radius of convergence. So what can we say about that? Do the coefficients that result do they still carry with them physical meaning, even though I'm not generating something that's going to be convergent? And the answer is yes. And actually, there's a interesting remark. Freeman Dyson in 1952 gave a physical argument that says that if one is solving a problem in quantum electrodynamics by means of perturbation theory, then the expansion that you obtain is necessarily divergent. Okay. So, but the thing is, of course, the summation that you have in your mind, it has to be different, right? The coefficients of the divergent series, well, those are going to turn out to carry asymptotic data for the function that you're trying to recover, and you have to look at it from a different lens, and specifically the lens of Borel or Borelic Hall summation. So the theory of resurgence, which is sort of what I work in, is under this heading. And we'll talk a little bit about that right now. So a key ingredient in Borel Hall summation is the Laplace transform. And most people encounter the Laplace transform as an integral, or not even you might not think of it as a contour integral. So we'll do it like this: f of p e to the minus px dp. So you can think of this as a contour integral along the positive real axis, but you can also vary the direction of the contour, assuming that the integral still makes sense, right? So if f is integrable along this path, and say it extends into the complex plane, and it's still integrable and satisfies a decay assumption at infinity, then we can deform this contour of integration. And in Borel Hall summation, we really work with a whole family of these operators indexed, or a continuum of them indexed by theta, depending on the direction. And ultimately, what happens is that we obtain an algebra isomorphism that allows us to take in formal objects, these formal, possibly divergent series, and return functions that satisfy the equation that we're studying. So we'll assume that capital F is analytic in a neighborhood of the origin. And then we'll recall the Borel transform, which for us acts on the space of formal series and 1 on X. This formal, I guess you could call it a ring or a differential algebra, the theory of resurgence gets into differential algebras and differential Galois theory and stuff like that. We will not talk about that here, but for our purposes, we're going to let x have integer powers, but the extending to non-integer powers fairly straightforward. So the rule, the term by term, or the action of the Borel transform on monomials is given by this, and it's still a formal object. Like we haven't promoted it to a function yet. And one thing you also might note is that the Borel transform is related to the inverse Laplace transform. However, if you think, so inverse Laplace transform will actually return a function, whereas this thing is still formal. And when we promote this object to a function, these will have different they will have different domains. Something to keep in mind. Okay, so we'll assume capital F, the germ of capital F around 0 was obtained by summing the Borel transform of a formal series, possibly divergent or factorially divergent, and the given formal object is denoted by F tilde. And one thing to note, if you don't work in the community of resurgence, it's very common to refer to the p-plane as the Borel plane.
So the F tilde is a function of x or p?
It's so the notation is kind of bad. It's just a series. It's a series. It's a formal series in x. So I probably shouldn't have even written of x. Right? It doesn't have. It's just.
Yeah, I understand. Okay, but it's an x thing.
It's an yeah, exactly. And also for your knowledge, the x-plane is typically called the physical domain, and you can think of the relation. You can think of it as being analogous to the position of momentum space in quantum theory. Okay, so we say f. Now, f is now a genuine function. It's analytic at the origin, and we say that it's Borel summable in the positive real direction if the following conditions hold. It admits an analytic continuation to an open sector containing R+, and is exponentially bounded at infinity within this sector, and is hence Laplace transformable along this contour. So we compute the Laplace transform of f to obtain a function now defined in the x-plane in this way, in the way that you expect. And we call f, little f of x now, the Borel sum of capital F along R+, and is related to the original series. And this is really the kind of the important or the essence of Borel summation and resurgence, that the original object carries with it the asymptotic data for the function on the physical domain, and that's and this can be done in other directions, right? So the process, in some senses, you're gluing these relations together to usually obtain a function that's analytic on a Riemann surface. Okay, and please, if there are any questions at any point, just ask them.
So the procedure is you start with the divergent series,
Mm-hmm.
then you transform the terms,
Yep.
add them up, and then get something that has this continuation. You take the integral transform, and you get an actual function
Yep.
that has that expansion.
Exactly. And there's a lot that we can say, and I really don't want to spend too much time on it. But the act of summing it up, when we think of when somebody gives you a convergent series, right? You usually already think of it as a function, right? But it's still sort of a formal object, right? So the act of summing over the subset of formal series that are convergent produces an isomorphism between this space of formal objects and analytic functions, right? And it's kind of a subtle thing. But then with Borel Borel-École summation, we extend this isomorphism to a wider class of series that are divergent, but they can still return functions that behave nicely with operations, differentiation, complex conjugation, and stuff. Okay. So F will a priori be holomorphic in a half plane, in a right half plane. And this can be seen if you've worked with Laplace transforms, really just kind of undergraduate complex analysis. Now, where the half plane starts depends on the exponential growth, the exponential growth of capital F. Okay, and we may deform the contour of integration from a ray along the positive real axis to another direction, so long as so long as all of the properties are satisfied along the way, for all directions along the way. And this amounts to analytic continuation of this function to this function. Yes?
So you said that the function f is related to the formal series f tilde by saying, like is a definition or?
So this relation. So it's not a definition. It's an asymptotic. It's a result of, if you're familiar with Watson's lemma, from complex analysis. Pretty much it says that if I know a function around 0, so let's say is asymptotic, and there's a series version, let's just do one with a monomial, p to the beta, and we'll say real part of beta is bigger than -1, then the Laplace transform of f is asymptotic to gamma of beta plus 1 over x to the beta plus 1, where this is so this is Watson's lemma. And I didn't state it precisely. So this is for, this relation is as p goes to 0 from the right. And then this will be as modulus of x goes to infinity. I think it's in a right half plane. So let's say real part of x greater than 0. Okay. This comes up over and over again, and and then, like I said, there's a series version of it. Yeah, is that clear?
But here, I mean, like as you said, like the formal series does not really mix. I mean, it's not really a real object or real function. So.
Well, so you can still have asymptotics from things that are not or you can have a genuine function be asymptotic to something that diverges, or to a series that diverges, because
that's exactly what's happening in this situation.
Yeah.
I mean, if you expand this Laplace transform, you get a divergent series usually. It's one of those things that it really takes a long time to get used to, or at least for me, because we as mathematicians we hammer convergence, from early on, and with asymptotics, what you're doing with these asymptotic scales is very different, right? It's instead of the limit that you're taking is not as the index grows, but it's as the argument varies, right? And so it's the asymptotic. I can just put that up here actually. I don't know if this is. So let's see. So definition, so f is asymptotic to a series ck on x to the k plus 1 to infinity as x goes to infinity if the difference, is
small o of x to the minus n minus 1 as x goes to infinity, and this is for all n. So, which just means that the limit so it's a statement that a sequence of limits satisfies a property, right? So whereas with convergence, right, it's that the actual sum as n goes to infinity, the tail necessarily decreases. And with asymptotic series, actually, it's one of the reasons why they're generally or usually divergent is that well, anyway, yeah, I don't want to get into that. Is this clear? Okay. Okay. So, all right, by Watson's lemma or integration by parts. So now we just have this thing, and this is the function. And I can generate from it an asymptotic power series. So, where the my scale. So this is called an asymptotic scale, x to the minus 1, where the set is called an asymptotic scale. And you can think of it as like your device for probing a problem, right? So so you can take 1 over integer powers of x and replace it by other things that still satisfy this ordering relation, right? And you'll still get an asymptotic scale, and you'll generate it's not called an asymptotic power series at that point. You'll just have an asymptotic series, but you can replace these by kind of wild things, right? Trigonometric functions or really whatever you want, and depending on the problem that you're solving. And okay, so by Cauchy's theorem, the growing powers in the derivative lead to factorial divergence of the asymptotic series, unless f is entire, which is rarely the case in applications. So in fact, we want singularities in the Borel plane and one of the reasons is that they carry with them important information about the problem, specifically the Stokes rays, and their location and type. So now we're thinking of singularities of capital F, singularities in the p plane. So all of those singular points are going to allow us to construct a unique solution to, say, an ODE, with a given ansatz in terms of these Borel summed objects. So you have this formal power series. I use this machinery, which is an isomorphism, and I return a function that will satisfy the given ODE. And yeah, that's really all I wanted to say. Okay, each singular point of f corresponds to a Stokes direction of the solution to the problem, lowercase f. So,
sorry, what's the factorial divergence?
Of factorial divergence. So if the coefficients, all right, that's good. If c sub k, there might be something else in here, but the dominant growth of the coefficients is proportional to a factorial of the index to the power of 1. And sometimes you can have geometrically growing components. I'm not sure if that's part of the same definition as, or if that's part of the definition of factorial divergence. So k factorial possibly times say,
Factorial means a factorial.
yeah, that's it. That's it. Okay, so in the 1920s, Norland noticed that if we perform this change of variables, we precompose with this log, we can transform this integral into an integral over the interval. Now, playing the same game, say integration by parts, we obtain an additional expansion, but now the scale has changed. No longer are we using one on integer powers of n or of x. We have these Polynomial symbols popping up, and that's because if you perform the calculation, the kernel or the kernel we're integrating against is not e to the minus px. It's this, and with every iteration of this process, we're changing the exponent. Okay.
And that's supposed to be the limit x goes to infinity, is it right?
So, oh yeah. For this one, yes, absolutely. Thank you. Okay. So, if we treat this as just a formal object for now, from here on out, we will call these objects classical rising factorial expansions, where we have these Polynomial symbols as our asymptotic scale. And if you do a little bit of analysis using Stirling's formula, we'll see that we have a factor of 1 on k factorial coming up. So now, if the asymptotic power series diverged, it's possible that this new object will be convergent. Okay. So most often in applications, classical factorial expansions have two major limitations. First being slow convergence, at best power-like, and that's just a statement about the remainder. And second, limited domain of convergence, and which is usually unrelated to the function we're trying to study, and it's generally a half plane. And moreover, the boundary of this half plane is separated by a positive angular distance from the important anti-Stokes rays. And these are all like results, right? We're just kind of taking for. I'm pretty much just we're quoting Norland's work from 1926 or something like that. So they're not trivial, but this is what we want to improve upon. Okay. So our new method of generating factorial expansions developed in our paper remedies these two issues, giving rise to expansions which converge geometrically in a cut plane. So what's necessary for geometric convergence? I kind of want to skip these the next few slides, if that's okay, to get to the actual results. Does anybody have an objection to that? I mean, it gives us a. Excuse me, can you say again?
We don't know what it is, so there is nothing can object to.
You can, just skip it and then we'll.
Yeah, because we don't know what
we don't know
object to say.
Okay.
We cannot object to prove either way.
All right. Okay, so how do we build geometric convergence into factorial expansions? As we mentioned, this lurch phi function. It's a function of three complex variables defined as by this integral in this domain C3. And it's probably not, or I'm sure it's not obvious if you haven't worked with it, that this is related to the Riemann zeta function and the polylogarithm. So for us, we're going to fix the second parameter s. I'm going to take it to be equal to 1. And we're going to perform this change of variables going into the u plane now. And in a similar spirit to what we were doing before, we transform the integral representation into 1 over the unit interval. And now here comes a lemma. And this is kind of a basic result, not trivial to prove from our paper. So using the notation z, boldface z sub minus for the non-positive integers, we have this representation of the Lurch function, again with the second parameter fixed, and the first input, this Möbius transformation in z. And so this series converges absolutely and geometrically in X. And what you'll see is that the first parameter is going to act as a it's going to act as some kind of wiggle room for our to force our expansions to do what we want them to do. The parameter or the variable of our problem of interest is X, but then if we or by using the additional parameter z, it allows us to kind of force the problem to go the direction that we want it to, if that makes sense. Okay, so this provides a prototype for geometrically convergent factorial series. And the Lurch transcendent will be a building block for our factorial expansions. Its presence almost appears native to these problems. So, like I said before, the strategy is to put the problem into or relate the problem to Lurch functions and then use this to generate the factorial expansion. That is valid in a well, okay. So before we get into the main result, we have this dyadic decomposition, which at face value might appear strange. We are representing a rational monomial this way, okay, in terms of a infinite series of transcendental functions. But the intent here is that we are going to, this is what's going to allow us to extract the Lurch functions and then ultimately use the rational the factorial representation from the previous slide. And moreover, the error for this behaves geometrically. Okay. So, all right, a sketch of the proof and a note just before. So, of course, you have to worry about the denominators in the series vanishing. And this occurs at 2 pi I integer multiples of 2 pi I take away 0 for the series, okay? And every one of those will cancel with the same singular point that's occurring in this term. And then the only simple pole that's not accounted for is the one at 0, and that's canceled by the rational function 1 over p. The proof is elementary. We represent the expression 1 on 1 minus x in terms of in this way, and we play the same game with increasing powers of 2, the difference of squares of increasing powers of 2, and we proceed with, for general n, with this representation, and then we do a change of variables, exponentiating or letting x be exponential of p, or letting x be e to the minus p on 2 to the n. We obtain this relation, and then if you look at the statement of the lemma, the result follows from this. Okay. Okay. So the Cauchy kernel, in a similar spirit to what we just discussed with 1 on p, well, we can perform the linear affine transformation with another parameter beta, a non-zero complex parameter beta, And this is going to give us a representation of 1 on S minus P, the famous Cauchy kernel, in terms of these dyadic expansions with this free parameter beta, free complex parameter beta. And this will appear in the main result of the paper. The purpose of beta is to control the direction of the singular points. So we're going to have liberty to place the singular points of this expansion, and then ultimately have liberty of placing the cut where the expansion is valid, defining the cut plane where the expansion is valid. Okay. Okay, so from here we can proceed to look at our exponential integral representation. So taking beta to be equal to pi I from the Cauchy kernel decomposition, and S to be equal to 1. We can integrate term by term. We obtain this. And performing a change of variables, or several changes of variables, actually, we obtain these integrals over the unit interval. Okay. And then we recognize the Lurch function sitting in all of these summands. Okay, so we have this representation. And then from the earlier lemma, we have the factorial expansion for the exponential integral. And this is the form that is kind of the general form of the main result, where we have a single summation and a double summation. Okay. And this expansion is valid in the cut plane, C minus the negative imaginary axis. And you see how the parameter beta, which was equal to pi I, controls where, or dictates where the convergence is valid. All right, it's pretty straightforward to perform this, play the same game with with Airy functions and Bessel functions. We have the specific computation for the Airy function in the paper, and we just have the Bessel functions with the index nu as a first and second, or Bessel functions first and second kind, as kind of we actually haven't done the calculation, but it's pretty straightforward since the Airy equation is related to Bessel's equation.
So I guess if I could just ask a question.
Yeah.
So these formal series that or these expansions that you're getting are, they have the Polynomial symbols as the sequence of functions as your scale.
Yeah, absolutely.
But at any finite level of truncation, you could rearrange that into, since y is going to infinity, it could just be powers, right?
So these are convergent expansions, right? So it's no longer like actually an asymptotic expansion. Right, so so this is valid for each y, right? So they're actually convergent series, and it's the factorial growth that you get from the Polynomial symbols that is competing with the growth from the gamma function that's allowing the series to converge. So we have some plots. So if you'd like, we can look at truncation, number of or truncation level in K and in M. You'll recall that those indices were here and also here. So different combinations will result in different errors. And here we have a logarithmic plot, or a plot of the log of the error, and shows how different combinations can produce different errors. And this is performed on the Stokes line of the exponential integral. And you'll recall that the Stokes line here, it's not actually Borel summable, along the positive, classically, it's not classically Borel summable along the positive real axis, so we defined it as integrating just below But we can perform Borel summation in such a situation, and that's where resurgence theory comes in. And you can either do it with that, or Ovidiu found a way to do it with distributions in the late 90s. Okay. Okay, so looking at the anti-Stokes line, in this case, for this exponential integral occurs on the negative imaginary axis. And we can actually see this transition in behavior from decaying to oscillations with a truncation of the previous series, which is pretty remarkable, I think, and also my advisor thinks that too. So no, it's amazing what you can do with rational functions.
So how many terms are there to get these?
I don't remember. Yeah, I don't remember. All right. So in the remaining time, I would like to tackle the main theorem of our paper and then also discuss the resolvent identity. I don't know if we'll have time to discuss the Painlevé equation, but that's okay. Just to make sure we're all on the same page, we're going to use the term function element to refer to a function satisfying these conditions. So we have a function that's analytic and defined in a cut plane, where L sub omega is a ray who's based, it's emanating from omega, traveling to infinity in some direction, and our function f is assumed to decay as p goes to infinity, modulus of p goes to infinity. That's it. And omega cannot be cannot be the origin. So we're going to make a few hypotheses. We have another complex parameter beta, and we assume that its argument is in the second or the third quadrants, and theta is an angle. I don't know if the term or the statement in the right half plane is actually precise or not, but theta and b satisfy this equation, or this relation that their sum is equal to pi mod 2 pi. Okay, and capital F is a function satisfying. It has at 1. It has exactly one singularity, an integrable branch point placed conventionally at 1, and it decays at infinity. So it satisfies this estimate, and is also locally integrable. What we mean by that is along, let's say, compact line segments in the complex plane. So give me any compact line segment, and it's L1 in that, along that set. Okay, and F is analytic in this cut plane, okay, and can be analytically continued through both sides of the cut. And finally, we will place ourselves in a position that one frequently finds themselves in such applications where we have a function that we would like to study, which is the Laplace transform of this given function. And now it's a Laplace transform, it's directional, along the contour with complex argument minus b, which is related to the given beta. Okay. So I have a little, and this piece, you'll remember with Laplace transforms, when you write one down here, it's for the classical Laplace transform along the positive reals, your domain of analyticity is a right half plane. As you vary the contour of integration to different angles, you're going to obtain tilted half planes of holomorphy, and the relation, the reason that is you have to make sure that this kernel, the exponential e to the minus px is actually decaying, because as p is complex, then the family of x's that such that this has real part greater than 0, it now has to depend on the argument of p. Okay. And this is just for illustrative purposes. We have our branch cut here, our singular point at 1, and our contour of integration. So the goal is to obtain a factorial expansion of f, the directional Laplace transform of capital F. Okay. And that's what this theorem does. So our function has a dyadic expansion for all x in this cut plane, okay, and it satisfies, or it's given by this, where the coefficients are written as integrals of the branch jump of f along the cut. Okay. So you remember we have the cut. And as we're actually, so there's a contour deformation that happens in here, but you take in the contour the resulting contour from the deformation is a Hunkel contour that's wrapping around the branch cut, and those coefficients are are given as integrals of the branch jump of the given function across this cut times these dyadic pieces, these exponential pieces. Okay. And the remainder satisfies or has this closed form where rho n0, rho lk, and r sub capital N admit geometric decay estimates in various asymptotic regimes of n at lowercase n, capital N, and L. The precise asymptotics can be found in the paper. And moreover, convergence of the previous expansion is uniform and geometric in this cut plane. Are there any questions?
So the Rn, this goes to 0 as n goes to infinity because it's convergent. Is that what you're saying? The
Yes.
side,
Yes.
the whole thing.
Yep. Whole thing goes to 0. But then with the various asymptotics, you can play with these three parameters and obtain different levels of accuracy and different with different numerical efficiencies, I guess. Any other questions? Okay. So the resolvent identities, or really the resolvent identity, well, there are actually two. Well, yeah, there are actually two of them. So these, or this process translates into decomposition of the resolvent of self-adjoint operators and also positive operators. That's in the paper. I'm not mentioning that here. In terms of samples of the unitary group that we talked about before, that the operator generates. And we'll recall the situation. So let H be a Hilbert space and A a bounded or unbounded self-adjoint operator. And let U sub T be the unitary evolution operator generated by A. So again, you write this down from the spectral theorem. And if lambda is a positive real, then we have, if we want to evaluate the resolvent along the positive imaginary axis, say, then we can represent it in terms of these this series of operators. And one thing that's kind of interesting, and I've been playing with a little bit, is that if you look at this, you'll recognize that each of these are resolvents.
and the resolvents of these unitaries. I've been trying to see, like, if that provides any physical, or if there's some physics sitting there. It seems like there is some physics sitting there. All right, and our convergence holds in the strong operator topology. And if we want to go to the lower half plane and evaluate the resolvent along the negative imaginary axis, we just have to take complex conjugates. And yeah, I think I will end there. I mean,
Okay,
Thank you.
let's thank Nick. Any questions for Nick?
yes. Oh.
No, you go first. You go first.
Can you just say something about how the resolvent identity is proven?
Yeah, I mean it's the dyadic expansion that we had before for the rational function and the spectral theorem and dominating convergence, and that's pretty much it. And you take a limit, and that gives you the identity.
So are there any assumptions on like the spectrum of the self-adjoint operator? Like does that
Just that it's self-adjoint. And I have a computation for the Laplacian with this that I'm putting together, or a self-adjoint version of the Laplacian. Yes.
So I wonder if you could just maybe show us your result for the P1.
Yeah, absolutely. So I mean the nuts and bolts are, or the quick story is that we have a rational approximation for tritronquée, and this method uses Padet approximation with mixed with Borel summation and some of these techniques as well, and gives us a means of generating the pole locations to very nice accuracy for tritronquée, as we can see here. This is the first 100 poles of tritronquée, of a tritronquée, and then also we have this contour plot, which is kind of neat. So here we're starting at a base point, and this is in the physical domain, starting at 1 minus I away from the pole region for tritronquée. And as we take steps of size 1 on 10 away from here in the positive direction, in the real and imaginary directions, here this is the log plot for the errors, and the error is really just the it's the operator of the differential equation applied to the approximation. So here we have order of 10 to the minus 20, 10 to the minus 60. Yeah.
And how does it compare with like the Fornberg-Weidemann, pole vaulting and thing for finding poles and so on?
I'm not sure. I will look. I'm not familiar with, or very familiar with that.
It's
so
worth looking at. It's
yeah.
It's like it's not you're doing you're doing convergent expansions and so on, and they're doing numerical method based on Padet approximation, but it's
Okay.
It's rational functions at the end, right?
Yeah. Yeah. I mean, we use Padet in here as well. I mean, it's such a wonderful tool, especially with Mathematica. I mean, it's very, very powerful. Anything else?
Do we have explicit formulas for the poles locations, or?
In principle, I mean, they are the poles of the Padet approximant, of a Padet approximant. So I think you could say that those are explicit.
Like you don't have location of the you just have approximation for the poles. It's not the exact location.
Yeah, exactly. But the error in the location is, we have control over that, and there are estimates, and the convergence, right? If you're familiar with Padet approximants, it doesn't converge pointwise. It converges in capacity.
So, but there are, because the capacitor for P1 in the Borel plane is straight, you know, the Green's function for the capacitor is the map to the unit disk, right? Because it's simply connected. There's some results in Stahl's work that tells us that. So we do have an exact representation for the Green's function. So I'm kind of still playing with all of this, and this is another paper for P1. It's definitely not complete, but yeah, it's been very, very interesting to work with.
Do you think you can use your method to give another proof of the, no pole?
De Brovin conjecture. I mean, we're talking. I mean, all of this started like 3 years ago, and it was supposed to originally, like, the project was supposed to be an elementary proof of the de Brovin conjecture, and it turned out to be a little bit more difficult than Ovidiu thought, and so it's morphed into this, and we've still been discussing applying it. We have been discussing applying this to that conjecture. Yeah.
Any other questions? Thank Nick again.